Hi everybody, sorry for the late announcement about this, but we're going to make today's lecture recording. So the remainder of this lecture after the announcement slide was recorded in a previous semester, but all of the content's still the same. So I think that it'll be essentially the same thing you would have got if we'd had this meeting over Blackboard Collaborate. Couple of announcements before we begin. First of all, for those of you who are in the civil engineering lab, remember we don't have any lab meeting this week. This is the week that you should be working independently and conducting the experiment that you've designed for the Hazen-Williams equation. So just as a reminder, those lab handouts are due Wednesday, tomorrow, by 5 p.m. And then you have all of this week between 8 and 5 to go into the lab and run the experiment. So if you have any questions about that or if there's any equipment issues, please do let me know. The second announcement for those of you, all of you, and not just applicable to the civil engineering students, but everyone in the class, homework 9 is available now on Blackboard, and so that covers more concepts related to the continuity equation, reservoirs, nozzles, cavitation, and some initial momentum questions. And so that's going to be due a week from today on Tuesday, November 10th. And so if you want to get an early start on that, I would encourage you. It's available now on Blackboard.
All right. Well, let's just refresh our memory about reservoirs. Remember, we've talked about reservoirs already with the Oahe Dam and the peak flow that they had. And we also have talked about the rise, the velocity that liquid levels may be rising. And I want us to tackle this one more time, just because sometimes thinking of it in terms of a flow rate that there's a rise in a place where liquid accumulation can occur is a little bit of a foreign concept. So there's water coming in at 11,300 cubic meters per second. And it's discharging at a lower rate, 7,080 cubic meters per second. So there's a net difference between the two. So we know straight away that the liquid level is going to be rising. But we want to know the velocity of that rise. And what we're given is the surface area of the reservoir at this particular moment in time. Now the way that reservoirs work is that the deeper they get, the larger area they cover, because the water continues to move upstream, and so the area of the surface increases. But at this moment, there is 10,360 hectares. And that's not a unit that most of us are probably familiar with, hectares. Anybody know what that is? It's 100 meters, maybe you are familiar, by 100 meters, so that's 10,000 meters squared. So what I'd like you to do is, just to refresh your memory on how this stuff works, find what is the velocity that it's rising in terms of meters per hour. All right, so we know the surface area of the reservoir, and we can easily calculate the difference between in minus out. Remember, that tells us accumulation. If there's more in than out, there's a positive accumulation, and that's the case here. We have 11,330 coming in, 7,080 going out, and I call that Q rise, because it's the rate of accumulation in the control volume that's causing a rise. And if out was greater than in, I might have relabeled that to call it like Q fall, because the liquid level would be decreasing to satisfy that imbalance. So the velocity that the liquid level is going to rise is going to be the rate of accumulation, Q rise, divided by the surface area. So we have 10,360 hectares. We need to convert that into square meters, and it's a lot. 1.036 times 10 to the 8th meters squared. So then the last step to find the velocity that the liquid level is rising, we have to have our Q rise divided by the area. And this is, V equals Q divided by A. So this is just application of the continuity equation. We have it in terms of meters per second, but if we want to know the rate that it's rising in meters per hour, because maybe that's a little bit easier to comprehend. Like I wouldn't know what 4.1 times 10 to the 5th meters per second looks like, but I can wrap my head around 0.148 meters per hour. So that tells you, if your house is how many meters above the water surface right now, it tells you how long you've got to evacuate. If the water level's rising. I guess I've got that show Ozark on my mind. They're always talking about how people were flooded out. Anybody watch that? The whole point of the show, obviously, is fluid mechanics. And it's some guys deeply offended by the electric company and how they flooded his ancestors and stuff like that. So the main plot is about this. So how could it be about anything else? That's the main plot of First Man, which I watched over the weekend as well. Fluid mechanics, the air over the wings, that sort of stuff. So it all comes back to fluids. All right, any questions on this before we move on? Well, let's revisit the orifice equation, because what we looked at before was just steady state. Remember, when you were in the lab, what we were ensuring was that the liquid level stayed the same. And the way that we did that in the lab was we had a certain flow coming in, and then we had water coming out from the orifice, but then there was also an overflow. That little tube that we raised and lowered, that overflow kind of controlled the liquid level, but it also made sure that there was always the same amount going in as going out. Like, it didn't flood. We didn't have any spillage over the top. But it's not always the case that you're going to have steady conditions. And one important application of unsteady flow is a storm event. When it rains, there's a sudden rush of water coming off of the pavement, coming off of vegetated areas, all of it headed towards receiving bodies like creeks and streams and rivers. And so that's a really important unsteady flow condition. And sometimes to try and mitigate flooding of rivers, what they'll do is they'll send water to stormwater ponds. And there's a really good example of a stormwater pond over by Target in Barbersville. As you go towards Target, it's on the left side. If you look next time you're going up there, it's behind a big chain link because it's so deep they don't want anybody to get in there and splash around when it's raining. But those stormwater ponds, the water doesn't stay in there permanently. There's an inflow and an outflow. And the outflow rate is determined by the orifice equation, because essentially you've got a big pond and there's a pipe, and sometimes the water is high, and when the water is high, the flow rate out through the discharge pipe will be high. But then as the liquid level falls, the storm is slowing down, discharge has been going for a little while, so now the H value is a little bit lower as it was before. And so now the velocity out of the pipe will be lower, and the flow rate out of the pipe is going to be lower. So it's important for us to be able to look at unsteady conditions where flow in doesn't equal flow out. And here's an equation, the orifice equation, where we apply it with the continuity relationship. We can come up with an equation that tells us how long it takes for the liquid level to fall a certain distance when the outflow is governed by square root of 2gh. So we're going to combine these two ideas together. And remember, the orifice equation originates from the Bernoulli equation. If we want to find the velocity of this jet that's coming out, we only have to compare the location here to the location of the water surface and apply Bernoulli's equation, because that'll allow us to account for how much pressure there is at that elevation, and that pressure goes from being potential energy into kinetic energy, and we've got the discharge out. So the orifice equation, as we talked about in lab, is derived from Bernoulli's, and so we're combining Bernoulli's equation with continuity to try and find out how long does it take for the liquid level to fall when we have, in this case, no flow coming in, because it's just a fixed amount of water, but we do have flow going out. So what we'll be doing is tracking the change of mass inside the control volume over time. Now, what we need to first of all look at is the rate of flow out through that orifice is V1A1. Okay, so there's a certain diameter opening In the lab, it was either 3 millimeters or 6 millimeters, depending on which equipment you were using. So there's a certain diameter opening that you can calculate the cross-sectional area from. So that's A1, is the area of this opening. And the velocity that it comes out, of course, we know we can determine that from square root of 2gh. So that is the outflow component. But then the change of mass inside of the control volume, what we're saying is we can track the mass in the control volume as it decreases by looking at the cross-sectional area of the tank. So this A sub t is a different area than the orifice area. The A sub t is talking about if we have a circular tank, then what is the cross-sectional area of that? So A sub t is the top view area of the container. And then dH dt is how quickly the liquid level is falling over time. Similar to what we just did in the previous example, but instead of the liquid level increasing, if we only have flow out, the liquid level will be decreasing. So some substitutions. For V1, we're going to substitute in the square root of 2gh. That's the orifice equation. And now we can rearrange the d sub t to the left-hand side and then integrate. And so now that d sub t becomes time. Now, the constants stay as constants. The tank area is a constant. It doesn't change. The area of the orifice is a constant. It doesn't change. 2g, of course, it doesn't change. But what did change? Here we had height to the 1/2 power because we had moved it over to the other side. And it used to be to the 1/2 power, but now when we move it to the other side, it's to the negative 1/2 power because it should be down here in the denominator, with 2g. So what we're saying is, in this step, we split the h to the 1/2 power, moved it to the other side, so now it's to the negative 1/2 power. But then when you integrate with respect to h, it goes from h to the minus 1/2 to h to the 1/2. So this tells you how long it takes for the liquid level to fall a certain distance. And so if we use as our limits at time 0, the height is some original height, then we can find out at a given time what the final height is going to be, or for a certain height that we're interested in, find out the duration between the initial height and the final height. So that's what this is solving for, and it's what we're going to, in the next example, try and calculate. Yeah?
On this upcoming homework,
Mm-hmm.
a problem that is almost identical to this. Do we have to derive the equation, or is it okay if we just use that one?
You can use this directly. You don't need to derive it. Okay, so let's try out this unsteady flow. The tank has a diameter of 500 millimeters, so that's going to give you the A sub t. The orifice opening is 15 centimeters, so that's going to give you the A1. The initial height of the water is 1.5 meters, and so that is from the center line of the orifice up to the water surface, 2.5 meters. Okay, now you got to be careful because these are always trick questions. It's just like a basic intelligence test to make sure that you can dimension your drawing and put in the right values for H naught and H. So in question A, it's asking how long will it take to fall 1.1 meters? So 1.1 is not H naught and it's not H. What you need to do is you have an initial height of 2.5 and it's going to fall 1.1. And so what is the final height after it has fallen 1.1? That's what you need to put in here for H, is the final height, not the fall distance. All right, so I'm going to pause this for a moment so you can calculate the tank area, calculate the orifice area, and then in part A, how long for it to fall the first 1.1 meter, and then, just for kicks, let's in part B see how much does it take to fall another 1.1 meter. So you're going to have a different H naught and H than you had for the first question.
We don't schedule until next week, do we?
All right, so we calculate the two relevant areas, and I got a question about, the wording of the orifice. It didn't necessarily say that it was a circular opening, so I changed that to make it more explicit that, yeah, it's a circular opening. So we calculate the areas, and then, kind of the dimensioning and interpreting the heights. So that means if the initial height's 2.5 and it's falling 1.1, then the finishing height at time t should be 1.4. So we want to find out how long does it take to go from 2.5 down to 1.4. Now, by the way, remember, this is all assuming no energy loss through the orifice. So if we wanted to actually observe this more accurately in the field, we need to apply a discharge coefficient. You've already learned about C sub D values, and so you could calibrate this orifice and find out what is the discharge coefficient, because it's not going to drain as fast as we think it is because of that whole discharge coefficient thing. But with that at the back of our mind, that this is assuming no energy losses, it would be 2 seconds. But actually, it's going to take a little bit longer than that to drain because of the whole discharge coefficient thing. Okay, so to fall 1.1 meters, 2 seconds. To fall the next 1.1 meters, there's going to be less pressure pushing the water out of the tank. And you've seen this, that when the liquid level gets low, the bathtub doesn't drain as fast. Or if you put a hole in a garbage can full of water, as the liquid level gets lower, the flow rate out decreases. And so that next 1.1 meters, it means that it's going from 1.4 meters down to 0.3. That's the starting is 1.4. The finishing depth above the center line of the orifice is 0.3 meters. So the areas stay the same, but the fall heights are different, so it's going to take longer, 3.19 seconds for that next 1.1 meters of fall. This equation is going to go in the FE reference manual. It's not there now, but it's going to be in the next edition, which comes out 2020. So keep your eyes peeled. Yeah, I'm going to see to it that this equation's in the next FE reference manual, so we can start writing questions like this, Yeah, we need to add some more unsteady flow questions. And the first step is putting it in the equation book. Any questions before we move on? All right, another application of the continuity relationship is flow through a nozzle. Here we have a combination. We've got, we have a manometer. And remember, a manometer is a place where we can use a fluid deflection to tell us about a pressure. And the fact that we have this liquid in the manometer with a deflection tells us that there's more pressure somewhere, and at another spot there's less pressure. So just by looking at it, can you tell 1 versus 2, which of them has more pressure and which of them has less? Where is there more pressure, 1 or 2? 1. And what's the clue that there's more pressure at 1? Yeah, if there wasn't more pressure, it'd be the same. But there's an imbalance there. That means that there's more pressure at 1. Now, the question is, does that match what Bernoulli's equation tells us? Bernoulli's equation says that if the velocity increases, the pressure will decrease. And that's what we see. All right, so all is right in the universe. The manometer kind of is behaving the way we'd expect it to behave based on Bernoulli's equation. So let's try and throw in some specifics here. If we know that the area at 1 is double the area at 2, we can use this first relationship of A1 and A2 to give us the velocities. We know the velocity at 1, that's somehow been defined or measured. So the velocity at 2 is going to be double that, because the area at 2 is half the area at 1. So here's Bernoulli's equation, which defines what's going on in the nozzle, but then it is the hydrostatic equation that defines what's going on inside of the manometer. And we can rearrange the hydrostatic equation and solve for P sub z using this formula. Remember the definition of P sub z, since it's been a while since we did any calculations with P sub z. Remember, P sub z is pressure plus gamma z. So what this is saying is that if you have P sub z1 minus P sub z2, then you get delta H gamma of liquid minus gamma of air. So this manometer is telling you the change in piezometric pressure between 1 and 2. So what is the delta P sub z, the change of piezometric pressure? What we're saying is that is P1 plus gamma z1 minus P2 plus gamma z2 is equal to delta H times the difference in the unit weights of the liquid. So we're combining two ideas together. And the unknown that we want to find is, what is the delta H here? Now, we don't actually know the pressure at 1 or 2, but we don't have to know it in absolute terms. We can just we can know what the difference in pressure at 1 and 2 is, because Bernoulli's equation will predict the difference in pressure. Bernoulli's equation says, well, you've got a difference in elevation between the 2 points. We know the fluid density, the fluid that's going through the nozzle is air. So Bernoulli's equation will tell us how the pressure is going to change because of the change in velocity. And continuity relationship tells you the change in velocity. So V1 and V2, well, V1 is given directly. V2 you get from the continuity relationship. And when I say the continuity relationship, that means Q in equals Q out, or A1 V1 is equal to A2 V2. So, the flow that goes into the nozzle is coming out of the nozzle. Now, of course, what we're assuming is that the density is constant in this nozzle. That's not our best assumption ever, but we're going to solve this problem assuming that the density stays the same between location 1 and location 2. If we knew a difference in density, if we could measure that, then we could improve our prediction a little bit. But what I'd like you to do is try taking a stab at what is delta H. How big will that deflection be in the manometer based on, we know the velocity is going to change. You can substitute into the Bernoulli's equation, but rearrange Bernoulli's equation so that you can substitute it into this delta P sub z. So rearrange this Bernoulli's equation so that on one side you have P1 plus gamma z1 minus P2 gamma z2. What's on the other side when you rearrange Bernoulli's equation to look like this on the left side? Do a little algebra. I've got some of the preliminaries up on the screen if you want to check, like the unit weight of air, our velocity at location 2, and so on. Okay, so with Bernoulli's equation, we just want to rearrange things so that we can get the difference in piezometric pressure, because that's what we're going to substitute into the manometer equation to solve for delta H. So we started off with the full Bernoulli's equation in terms of pressure instead of in terms of pressure head. Ordinarily, I write it in terms of pressure head, because like in civil engineering applications, that's often what we're solving for. But here, what we do is we group. So you can see for P1 plus gamma Z1, we group that together, and that's P sub Z1. So the piezometric pressure at 1 plus the velocity head. Oh, well, it's not velocity head. I guess this is the velocity pressure at 1. And then also at 2. So then delta P sub Z is just P sub Z1 minus P sub Z2. So that's on the left-hand side of the equation. On the right-hand side of the equation would be V2 squared minus V1 squared multiplied by density divided by 2. So we put in the actual numbers we know, like the velocity at 2 that you calculate from continuity, the velocity at 1 that's given, the density of the air, which was given. So it means that the change in piezometric pressure between location 1 and location 2 is 1435. So what is piezometric pressure again? It's like the change in pressure already accounting for the effects of the elevation difference. Because sometimes a pressure change is because a point is higher or lower. But this piezometric pressure is accounting for other factors, like in this case, the change in diameter and the increase in speed. So this piezometric pressure is telling us how much of that pressure is because of the decreasing diameter. So then we can substitute that into the manometer equation. We rearrange the manometer equation in terms of the unknown, delta H. And it looks pretty easy when you see it there before you, but it sometimes takes a little bit of extra thought to get there in terms of, like what are the principles I know and how does it combine together. But, in this picture, like what are the clues? Well, the clues are that you have static conditions in the manometer tube. And if you've got static conditions, then you can just use the hydrostatic equation. And that's essentially what this manometer equation is it's the hydrostatic equation relating conditions at 1 and conditions at 2. Although this was given to you directly, you could have just started with the full hydrostatic equation and ultimately arrived at the same thing. Do I need to leave this up for a minute to copy down, or anybody have questions? All right. Did we already see this picture before this so far this semester? All right, so you already remember that you don't have to be told that this is boiling water, because you've already heard that in lecture before, that this is boiling water, so you remember it because I told you. You wouldn't have known otherwise. This is boiling water. But remember, what the discussion we had was that there's two ways to boil water. There's heating it up to increase the vapor pressure of the liquid until it matches the atmospheric pressure. So that's option 1 for boiling water. And boiling, like what is boiling? It's not like oxygen is forming when you heat it up. This isn't air. It's not air. It's liquid vapor. So it's vapor H2O. And so you heat up this water to the point to where vapor begins to form, and then it rises to the surface and goes out. So that's option 1 for vaporizing water. Option 2, remember, was to put it in some sort of an environment where the atmospheric pressure surrounding the liquid is really low. So instead of increasing the vapor pressure, what we do is we could leave the vapor pressure alone and just decrease the surrounding pressure until the two are equal, and then it'll start to vaporize. So we saw this figure that related temperature and the pressure, the vapor pressure of a liquid. And we saw that water can boil at 100 degrees Celsius because its vapor pressure becomes equal to atmospheric at that temperature. And by the way, that's no coincidence, of course. By definition, they set 100 degrees Celsius to be equal to the temperature required to boil water at sea level. That's why they used that scale. And 0 isn't coincidentally the temperature that water freezes at. That's how they decided it would be 0. So what is kind of filling in the blanks, though, is the vapor pressure of water in between. So the reason I bring it up is that one of the applications of Bernoulli's equation is, remember that when water speeds up, its pressure decreases. And there's a point at which that should begin to make us a little nervous, because the pressure of the water that's going through a conduit, if the pressure gets low enough, then these little water vapor bubbles can begin to form. And they can be quite destructive. Let's use this as an illustration. Now, the water inside of the tank that's on the left is just atmospheric pressure, and so, you know, at the water surface, the pressure is 0, gauge pressure. If the water is moving very slowly through this pipe, then we're going to have this top blue line represent the water is moving slowly. There is a little bit of a pressure decrease as we go through this section where the diameter is lower, so the velocity will increase, but it's not increasing very much because it's slow-moving flow. So the pressure dips a little, but then it recovers as the diameter increases again. You'll notice that it's not recovering all the way. It's not going as high as it was before. So it seems that they're accounting for a little bit of energy loss through that converging section. All right, so now let's increase the velocity a little bit. Let's maybe through a valve downstream, we're controlling the flow. So now we're going to allow the water to move a little bit faster through this pipe. So the velocity is a bit faster. That means the pressure is going to drop lower, because the bigger the difference in velocity between point 1 and point 2, the bigger the change in velocity, the bigger the change in pressure. Now we've drawn the dashed line here kind of to scale in a sense. And the scale that we're using is that when that dashed line goes below the actual water surface, that is when we say that we have a negative gauge pressure. That actually the pressure is lower than atmospheric. Because, you know, the pressure as we go down in this reservoir, the pressure is increasing according to the unit weight. And so there's some positive pressure associated with our depth. But what this scale drawing is meant to illustrate is that the velocity can be going so fast through this throat of the nozzle. The velocity can be so fast that the pressure goes really low. And the pressure on an absolute basis is still above 0, but on a gauge basis, it's below 0. And so sometimes we solve these problems on an absolute basis because, you know, we have vapor pressure on an absolute basis. These pressures in terms of pascals, so the vapor pressure of water at 20 degrees Celsius is 2340 pascals. That's absolute. That's relative to 0. That's relative to gauge, a vacuum as the 0 point for these vapor pressures. All right, so let's zoom in on the situation. If we have the water moving slowly, then maybe just a little bit of vapor bubbles could form. But if we move the water fast enough, then there's a lot of these little vapor pockets. And the problem is that they wouldn't necessarily cause any damage if the water stayed moving fast and the pressure stayed where it was. But you'll notice that in this diverging section, the pressure is going back up again. And so these little vapor pockets, they get crushed by the increasing pressure. And as they collapse, then it sends a shock wave through the water, because you have water rushing in to fill the void of that vapor pocket, and it's doing so very quickly. And so the water kind of collides in the vapor pocket from all directions, and then it sends a small shock wave out through the water. And even though the volume is small, the increase in pressure is very high because it's filling in that void very quickly. And so,
Is that true when it's just like a sudden change in velocity as compared to like just a gradual?
Well, it could be a gradual change. One of the places that people talk about cavitation the most is in submarines, like the propeller on the back of a submarine. And the cavitation occurs like when the submarine is accelerating and then when it's also moving at high speeds. But it doesn't necessarily have to be at high speeds that there's cavitation. The cavitation can form either because of a velocity change or because of a big absolute difference in velocity, like on the front side of the propeller versus the back side of the propeller. There would be a pressure difference between the two. So I don't know if that addresses your question. What was like the
Thinking about this sudden change in the velocity.
Mm-hmm.
That creates like a bigger shock wave.
Yeah. If this was a really gradual transition, it's possible that those vapor pockets might collapse more slowly than if it's a more sudden transition. And that would probably be less problematic from a materials scour standpoint. What we'll see here is that change in pressure and the shock wave that it sends often occurs in pumps near impellers, because impellers are locations where the pressure of water changes very dramatically and quickly. Like this pump diagram is showing that what it's doing is it's sucking water from an origin, and here on the suction side of the pump, the pressure is low. But then suddenly you have a pump adding a lot of energy in the form of an increase in pressure, and so that rapid change of low pressure to high pressure can cause cavitation depending on how long this suction side length is and the elevation difference between the reservoir's water surface and the physical location of the pump. So there are factors we can kind of control and keep an eye on to prevent cavitation, but when it occurs, it causes quite a lot of damage to pumps. So let's try and predict whether there will be cavitation. And the criteria for yes versus no on cavitation is the pressure of the water above or below the vapor pressure of the liquid? If the water pressure is below the vapor pressure, then yes, there will be cavitation, because that means that you're not holding the water down with the surrounding pressure, and so some of those molecules can go into the vapor phase. But if the vapor pressure is less than the water pressure, then there will not be cavitation. So here, the continuity relationship is what we can use to calculate velocities. In this case, the velocity is just given directly. So put it into the Bernoulli equation to predict what will be the pressure at 2, and then compare that to the vapor pressure of the water. We're assuming this water is at 60 degrees Celsius. Yes, there will be cavitation. Let me... All right. So the water's going from 20 to 45 meters per second. The pressure started at 814 kilopascals, which ought to be plenty. Except for that, there's a pretty big change in pressure. And I like to group it so that I can see, for example, how much pressure head do we have to begin. So there's 84.41 meters of head to begin with. And there's also some velocity head at location 1. But the velocity at 2 is going to be so high that at location 2, the pressure of the water is only going to be 15,332 pascals on an absolute basis. So 15,332 is less than the vapor pressure of water of 20,000 pascals, and so therefore, yes, there will be cavitation. So it could be potentially risky. In hydraulic engineering, we'll go into more detail identifying some of the factors that you can keep track of to ensure that cavitation doesn't threaten the equipment that you're designing. One of the historical cavitation issues that kind of illustrates the importance of it was this Glen Canyon Dam back in 1983. And I think I already showed you these pictures, right? Where what happened was the vapor bubbles began to form, and it caused a little crack, and that small crack got larger, and it started to scour and erode the material. And eventually what happened was it threatened the dam so that that spillway, you can see that the location of it is in close proximity to the dam, so if it starts to scour and actually gets into the dam structure, then the whole thing could fail.